Hello, hello.
Hello, sir.
Is my voice audible?
Yes, sir. It's audible. Good
Okay,
evening, sir.
good evening. So I can see only you have joined. Mm, So, so how many were there last class?
So many students are there, but two students have joined.
Yeah, okay. So maybe we'll wait for 5 minutes.
Sir, which paper will you teach today?
It is condensed matter physics.
Okay.
Condensed matter physics.
Means
MPH
MPH.
0, MPH
Mm,
12.
Okay, okay. Thank
So we'll wait maybe 5 minutes and then we'll start. Huh?
you. Okay, sir.
Okay. Good evening, class.
Good evening, sir.
Okay, one more has joined, right? Two more has joined. Okay. All right. So myself, Dr. Saroj Kumar Patra. I'm an assistant professor of physics at MPC Autonomous College, Baripada, and I'll be teaching you condensed matter physics, MPH-12. So we'll have the class today, tomorrow, then on 24th and 27th for this paper. Let me share my screen and then we will start. So is the screen visible to everyone?
Yes, sir.
Okay. Okay. So my screen is visible, right?
Yes, sir.
Okay. Okay. So just for record, I will be teaching MPH 012, which is condensed matter physics, and myself, Dr. Saroj Kumar Patra. And I guess all of you have the study material with you, right? Uh, the block 1, block 2, and block 3 of condensed matter physics, is it?
Yes, sir.
Okay, that's good. So going to that part, let me come to the study material. This one, yeah, I don't know. Somehow there is a problem. So now it is visible to everyone, right? The study material, block 1.
Yes, sir.
Okay. So as all of you can see, we'll be starting with block 1, which is uh, then lattice dynamics, and yeah, so lattice dynamics, thermal properties. So starting with crystal structure, uh, I would suggest all of you to open that page, hard copy, with so that it will be easier for you to understand. So, along with this material, if somebody is interested to read extra material, I would suggest the book by Charles Kittle, Introduction to Solid State Physics by Charles Kittle. So I might be following few of the diagrams from there as well. I'll be showing it. So starting with crystal structure, as the course itself is telling condensed matter physics. Initially, it was called solid state physics, but later on, other than solids, there are some condensed form of material which also have similar dynamics. So it is the general part subject would be condensed matter physics. And in the first one would be crystal structure, the structure of material. How exactly we will quantify, or we'll try to understand what exactly that material is. And for that purpose, uh, as you can see, uh, in this part, you will basically be classify solids as whether the solid crystalline, polycrystalline, or amorphous, and identify different types of geometrical symmetries. So we'll discuss a little bit about what a symmetry means and state characteristics, features of different types of symmetries, then draw various crystal geometries and categorize them into something called Bravais lattice. Mm, so determine symmetry elements of a crystal from a geometry. So how exactly we'll determine the symmetry element? Then calculate the atomic packing fraction, uh, because the whole solid is not full of material, but there will be some empty spaces. So that will determine the packing fraction, and explain the correlation between density of material and crystal structure. So which material is dense and why? And also we'll try to understand the cubic crystal and determine their Miller indices. So, so starting with structure of solid. Structure of solid, as we can see, it's basically, uh, if we broadly try to categorize, it will be crystalline, polycrystalline, and amorphous. So, uh, crystalline, as the name itself is telling, you will try to see crystals, and amorphous is somewhat like a powder form, and polycrystalline is somewhat in between. So we can possibly, like if you have seen like sugar cubes, or mostly when somebody says crystalline, it is sugar which comes into our mind, sugar cubes or sugar crystals. And amorphous, we all know this talcum powders that we use in summer season, right? So that is in powder form. So what exactly differentiates is the order, is the order of the structure within the material. Because let's say there could be sugar powder, there could be sugar crystals, there could be salt powder, there could be salt crystals. So it is the form, the solid form, which is different, and that form is basically defined by the ordering in the crystal. So crystalline solids have highly ordered structures in which atoms are arranged in a repeating manner, extending in all three spatial directions. So what will happen? That means if you have one mm, uh, crystal, let's say somewhat like looking somewhat like this, then this uh, unit itself will be repeated in space over large distance. So over large distance, it will be repeated in case of a crystal, as you can see in this figure. But in case of a powder, you will hardly see any kind of ordering. There will be, so this is highly ordered. and this is no ordering. Here it is no ordering. Sorry. So polycrystalline is somewhat in between. Polycrystalline is somewhat in between. So there will be short range ordering. So most of the time, the material we see now in our day-to-day life is polycrystalline. But if we are um, looking for perfect crystals, then those are a little bit expensive. That will come to know later on. Few of the properties we'll try to concentrate on this table. So crystalline, the atomic arrangement. So these are the three types of materials: crystalline, polycrystalline, and amorphous. And what are the properties we'll be talking about is atomic arrangement. Atomic arrangement. So atomic arrangement wise, periodic and long range order. Crystalline has periodic atomic arrangement and long range period atomic arrangement. And amorphous is short range order. So this is long range order, this is short range order. And uh, polycrystalline is somewhat in between, but the important factor is it will have something called grains, small grains. So in one grain, there is ordering, but these small grains will be randomly oriented. So crystallites, which are small grains. So you can imagine in case of a polycrystalline, so there will be like certain region, another region, another region, another region. So in each one of them there will be ordering, but these orders, these crystallites will be randomly oriented. They will be randomly oriented. So that's why this is crystallites, small grains with random orientation. Then we come to mechanical properties. Mechanical properties, you can see crystalline, they have high strength of mechanical properties. And amorphous is very low strength, as we can expect. Uh, and polycrystalline is somewhat in between. So here it is high, here it is low, and here it is somewhat in between. Electrical and thermal conductivity. Electrical and thermal conductivity. So for a crystalline material, for a periodic arrangement of atoms, for periodic arrangement of atoms, the electrical conductivity is high. The electrical conductivity is high. Whereas for polycrystalline, the electrical and thermal conductivity is very low. And of course, polycrystalline is somewhat in between. Examples: diamond is a perfect crystal. Quartz is a form of glass actually, but it is the crystalline form of glass. Table salt, as I was telling, salt. Um, uh, um, Other than that, if I can tell something in Odia, like we call spotica. So there is like this alum, aluminum oxide, alum is also fitkiri jota kaunte. So that we also get in a crystalline form. Whereas amorphous is glass is amorphous, rubber is amorphous, plastic polymers are amorphous, powder form. And steel and aluminum, these are somewhat in between. These are somewhat in between. So these are not perfectly crystalline or neither amorphous. They are somewhat in between. Is this part clear to everybody?
Yes, sir.
Okay.
Sir, but diamonds are not having good electrical conductivity. They are insulators.
Yes. See, not all crystals are good conductors of electricity. Okay, there are semiconductors which are perfectly crystalline, but unless you dope them, they will not be conducting any electricity. That will come. But it is in general, suppose one material is in general conducting in nature. Okay. Suppose we take a material which is in general conducting in nature. Okay. And then if we consider its crystalline form and amorphous form, then we will see that the crystalline form has a higher electrical conductivity and amorphous form has lower electrical conductivity. Is it clear?
Sir.
Okay. So I'll just switch in between. Let me show you few diagrams from Charles Peter. Let me come to that. Uh, what is it now? Yeah. You can follow this book also. This is kind of considered to be the Bible of solid state physics or financial material physics, the starting book. Uh, yeah, as you can see from this figure is visible to everyone, right?
Yes, sir.
Yeah. So as you can see, the picture in the lower part, the picture in the lower part is here. You can see it's kind of a crystal. Huh? And for crystal, what happens? You once you start cutting them, and you want to see using a microscope or even a a instrument where you can see almost the unit cells. Then you will from surface you will see they're smooth, but as you go down, as you look deeply inside the material or the sample, you'll see that there are building blocks like arranged like this. So that you can see. So these are something called unit cells. Unit cells are nothing but the smallest, you can think of smallest element of a solid whose repetition will produce that solid, whose repetition will produce that solid. Suppose I'll draw and explain, but this is how a crystalline solid will look like. Okay. So now, as you can see over here also, the periodic array of atoms, array means arrangements, right? So periodic arrangement of atoms will give rise to a crystal, periodic arrangement. So the important part is periodic arrangement. Huh. Let me highlight something here. Uh, mm, a crystal is formed by adding atoms in a constant environment, usually in a solution. Possibly the first crystal you ever saw was a natural quartz crystal grown in a slow geological process from silicate solution. Huh. Quartz, most of the time we have seen the first crystal, I would think, is either the salt or the quartz. Huh. So how exactly these how exactly these crystals are understood? We can we understand that there will be order, long range order, short range order. Uh, so, but to understand it, how the crystal is made not from physical point of view, but from structural point of view, we need to understand what the materials least element or the smallest element whose repetition actually is creating the crystal. Let me explain that by drawing it. What is happening? Let me create a new. Is it visible?
Yes, sir.
Okay. So let me write it down. So suppose we'll take for example NaCl, NaCl, which is our salt, right? Common salt. And if uh, we see a uh, crystal of the salt, then how exactly the smallest element would be called the unit cell. Okay. Repetition of unit cell, if we repetition of the unit cell will produce the crystal. Okay. Now suppose the smallest element is somewhat like a cube. Okay. So then what will happen? I will make another cube. I will make same direction. Again, I will make another cube. In the lower, I will make another cube. And I keep on repeat the same element, which is this. By element, I means the unit cell. This will produce the crystal. Okay, but to one, when I say smallest element of the unit cell, I'm not talking about atoms anymore. It's like the building block. So if I give an example, suppose we are making a house. We are making a house. Element or building block we are using is a brick, right? Of course, we are using cement and we are using sand and a mixture and all, but the element is bricks. By adding bricks, we are making the wall, right? So similarly, you can think of unit cell like a brick. But mathematically, we need to understand how exactly we are making this crystal structure. For that, we need to uh, write something like this. Crystal structure, this is made up by something called lattice plus basis. Okay. So this lattice is nothing but mathematical arrangement of points. Okay. Mathematical arrangement of points. And this is atom or group of atoms or molecules. Okay. So what do I mean by lattice? Let me draw uh, a simple lattice, square lattice or a rectangular lattice. A rectangular lattice. Okay. So what I'll do, I'll take a point here, 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 point here. So how exactly these points, if I ask how exactly these points are arranged, they are arranged in a rectangular manner. So along this direction, the separation is A. Along this direction, the separation is B. So the smallest element you can think of is like this, or to a point you can think of like this. So in one rectangle, that is one point, or you can think 4 points are making one rectangle, and each point is shared by 4 rectangles. Okay, so one point in one rectangle. Okay, now these points are called lattice points. These points are called lattice points. Lattice points. This is purely mathematical arrangement. Okay, but if we attach basis to each lattice point to make the crystal. Okay, so what will happen? Let's say I'm making NaCl crystal. Let's say I'm making NaCl crystal. Okay, so what I will do? Let me write. Let's say I will make my NaCl symbol is let's say alpha. Alpha is my NaCl symbol. This is purely hypothetical. I'm making alpha is my NaCl symbol. So what I will do? I'll write alpha, 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 like this. So this is a crystal now. So initially we talk about points. Initially we talk about points, and now we are attaching to each point. We are attaching the element or the basis. This is NaCl is called the basis. Okay, is it clear?
Yes, sir.
Okay, I'll take the two couple of minutes break. Uh, get a sip of water, and then I'll come back. Okay. Okay, coming back. So next we'll be talking something about uh, symmetry. Symmetry. Right? So symmetry is very much important to understand crystal structure. Symmetry is very much important in understanding crystal structure. So there are different kinds of symmetry, something called translational symmetry, rotation symmetry, mirror symmetry, inversion symmetry. Okay, so let us try to understand. Here, as mentioned above, it is telling crystalline solids are characterized by ordered symmetric arrangement of atoms and molecules. So crystalline elements, solids are characterized by ordered symmetric arrangement of atoms and molecules. This order is governed by geometrical symmetry. This order is governed by geometrical symmetry. An object is called symmetrical if an operation transforms the body into itself. This is very much important. Okay, this is very much important. Let me. So an object is called symmetrical. An object is called symmetrical if an operation or movement or transformation transforms the body into itself. So arrangement, whatever arrangement we had, we operate with some kind of, I mean, we can rotate it, we can translate it, we can invert it. But if we are getting back to the same element, then only it will call symmetrical with respect to that operation. Okay. In other words, if an operation leaves the object invariant, it will not change. It is called symmetric object. I'll give a very crude example. Take the example of a sphere. If you take a sphere and you rotate it, you will still see the same sphere. I mean, the shape and size will be the same, right? The way we see, measure and look at the sphere, the radius, the directions, and all will be the same. So a sphere is symmetric with respect to rotation. If you rotate it, it will be same. But if you, let's say, you take an example of rectangle, you take a rectangle. Huh? Let us say you take a rectangle, you take a rectangle, huh, and then you try to rotate it 90 degree. Rotate, rotate 90 degree. So then the way the rectangle was earlier, it will be changed. So its longer axis will become a smaller axis, and smaller axis become longer axis, right? So with that, we understand that the rectangle is not symmetric with 90-degree rotation. So it is not symmetric in that sense. Whereas if we take a mirror, then it will be symmetric. So the basic idea is an object is called symmetric or symmetrical if an operation or movement or transformation transforms the body into itself, or the object remains invariant under that. Okay. The symmetry operations are classified as translation symmetry and point symmetry. The point symmetry is further categorized as reflection in plane, inversion about a point, and rotation about an axis. Okay. So what are those? So there are symmetry operations if you consider. First one is translational symmetry. Translational symmetry. Next is point symmetry. Translational symmetry and point symmetry. Then again, point symmetry is classified into three types. Into three types. One is reflection in a plane. Reflection in a plane. This is number one. Number two, inversion about a point, inversion about a point, and rotation about an axis, rotation about an axis. Okay. The operations such as translation, reflection, inversion, and rotation constitute the elements of symmetry. So, what are the elements of symmetry? The elements of symmetry are translation, reflection, inversion, and rotation. Okay. Let me draw and explain little bit what are these four translation, reflection, inversion, and rotation means. Okay. Let me come to, yeah. So let me come here. So number one is translation. Translation symmetry. Number two, reflection. Rotation. And number five, inversion. Reflection about a plane. Reflection about a plane or in a plane. Rotation about an axis. About an axis. Inversion about a point. Okay. Translation means what? Suppose one object is here. Let's say one object is here. Okay. I'm taking the object to be a cuboid. I'm taking the object to be a cuboid. Translation means what? I'll simply move this cuboid by a distance, let's say d, or along this direction by a distance d. So still the object will look the same. Object will look the same. Hmm. So in that case, I'll call that this cuboid is symmetric about translation. About translation. Now, what does it mean when I say translation symmetry in a crystal? Translation symmetry in a crystal. That is very important. So let us take, for example, a two-dimensional lattice. Two-dimensional lattice means I'll just draw like this. So I'll draw lines like this and like this. Okay. So this is a two-dimensional lattice. So if let's say I call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and so on and so forth. My point is, if I move from cell number 8 to cell number 11, if I just move along X direction, or I move from cell number 8 to cell number 14 along Y direction, then the crystal itself is not changing. It still looks the same from all directions and point of view. It looks the same. So that's how I mean translation. That's what I mean when I move my point of observation from one cell to another cell in a translational direction. Okay. So this two-dimensional lattice is invariant under translation. All right. Next one is reflection about a plane. Reflection about a plane. Okay. Reflection about a plane. Is it clear? Whatever I'm talking, is it clear to everybody?
Yes, sir.
So reflection about a plane, that means it is as if, suppose I have an object over here. Okay. An object over here. What I will do, uh, I will, let's say, uh, make one DOM over here, another DOM over here. And I put a mirror over here. I put a mirror over here. When I see this same object on this side, what I will see? What I will see? I will see somewhat like this, right? I see somewhat like this. And this part will be somewhere here. And this part will be somewhere here. So this objects are not same, right? Are they same? No.
No.
Here I am seeing this bomb on the right corner. Here I'm seeing on the left corner. Okay. So it is changing. It is changing the object. So if I take a mirror image and still I get the same thing, then I will call it symmetric about a reflection. I'll tell another example where a mathematical example, for example, let's say, let me draw y is equal to x square. Y is equal to x square curve. So this is somewhat like all of you have done earlier, hmm, somewhat like this. Well, this is my 0 point, let's say. So now, if I take this is y-axis, this is x-axis. If my mirror is y-axis. So then on this part, once I take a mirror, it will be this part. So then, if I take mirror of this one, it will fall this one. So once y-axis becomes a mirror, the curve remains same. The curve is not changing. So that's why y is equal to x square is symmetry with respect to y-axis. Y-axis for reflection. Okay, is it clear? Is the reflection part clear to everybody?
Yes, sir.
You can interrupt me in between. That is fine. Wherever you are not able to follow, you can interrupt me. That is okay. All right. Rotation about an axis. Rotation about an axis. Let us try to understand what is rotation about an axis. Okay. So let me draw a three-dimensional one. So let's say this is my x-axis, this is my y-axis, this is my z-axis. Suppose I have an object like, let's say, similar one, but a three-dimensional one, a bowl shape, a bowl shape, whose axis is basically your z-axis. Okay. Now, if I rotate the bowl about z-axis, if I try to rotate this bowl about z-axis, suppose I rotate this direction about z-axis, the bowl will look still the same. So it is symmetric about, it has a rotation symmetry about z-axis. But the same bowl, if I try to rotate about y-axis, how exactly it will look? At some point, it will be somewhat like this, right? At some point, it will be somewhat like this. So it is not symmetric. It is not symmetric about y-axis. So if I rotate, so this bowl, whatever I have drawn, is symmetric about z-axis, but not symmetric about y-axis. Clear? समझते ओडिया আছে নাকি other than ओडिया আছে? Anybody other than Odia speaking? All of you understand Odia, or is there someone who cannot understand?
Yes, sir, Odia.
Odia. Okay. So just I'll be following telling you English, but just for few examples. माने तमे गोटे ऑब्जेक्ट को जदि गोटे एक्सिस अराउंड रे रोटेट कला परे भी जदि ऑब्जेक्ट ता सेम देखा जाउची ताले तार सेही एक्सिस अराउंड रे तार रोटेशनल सिमेट्री अछि, ହେଲା। ଆଉ ଯଦି ତମେ ଲେट्स से गोटे मिरर नहींच आउ गोटे ऑब्जेक्ट को से मिरर रे रिफ्लेक्ट कला बेलू इमेज जोटा आसुची सेटा ठीक ऑब्जेक्ट भलिया ही देखा जाउची ताले से जो प्लेन टा रहिला मिरर टा रहिला ताले ऑब्जेक्ट रो से मिरर सहित गोटे रिफ्लेक्शन सिमेट्री अछि आमे कहबा सहित ओके आउ जदि गोटे ऑब्जेक्ट को मु धरा जो भुवनेश्वर रे रखिछि ताकू मु नै आसिली बालेश्वर को किबा कटक को ताहले जदि सेम भलिया देखा जाउची से तार किछि शेप साइज किछि चेंज हो नै ताहले तार ट्रांसलेशनल सिमेट्री अछि बुझी होला एती कथा
Yes, sir.
okay right then we'll move over to what is called inversion symmetry. Inversion symmetry means what is inversion symmetry? So x y z point will go over to minus x minus y minus z. So that is called basically your inversion. Let us try to draw it. Let us say we have a three-dimensional axis system. Hmm, hmm. Let us say this is my x-axis, and this is my y-axis, and this is my z-axis. All right. And I take a point somewhere here. Take a point somewhere here. Hmm. So then what will happen? If I try, well, this figure is not telling much. Uh, so this is in first quadrant. If I try to let me maybe draw it a little bit differently. Uh, let's say the point is somewhere here. So then I this point. Hmm. So this is the coordinate is. If I try to write down the coordinate, this is x, y, and z. Inversion symmetry means so x will go to minus x will go to minus x, y will go to minus y, and z will go to minus z. So then it will be somewhat here where the coordinates are minus x, minus y, and minus z. Okay, minus x, minus y, and minus z. Another diagram I can say is let's say this is my x-axis, this is my y-axis, and let's say z-axis. Z-axis is uh, z-axis is um, out of the paper. Okay, so it is facing upward, facing upward. Then any point I take over here, any point I take over here, that will be x, y, and z. So that will move over to where x will go to minus x, y will go to minus y, so somewhere here, but in the down plane. So that will be minus x, minus y, and minus 2. Okay. If I come back to this rotation, what happens? The angle theta is involved. The angle theta is involved. Like if my angle of rotation angle is theta, rotation about z axis or theta z, then it will be symmetric with respect to that operation theta z. Here the operation is x y z going to minus x minus y minus z. Let us go to the study material. There we'll try to understand how this is. All right. So what is translational symmetry and periodicity? Translational symmetry and periodicity. Refer to figure number 1.2. This one, figure number 1.2, and consider the triangle PQR. So PQR, this triangle PQR, whose base QR has a length A, base QR, this QR has a length A, QR has a length A. You may note that the translation along the line AB, along the line AB, this is the line. Along the line AB, uh, by distance A keeps the figure invariant. Huh? So what exactly it is telling you? You may note that a translation along the line AB by a distance A or its multiple keeps the triangle invariant. It looks the same. It looks the same. We express this observation by saying that the figure possesses translational symmetry. ଯଦି A ଆମେ ଗୋଟେ ଏଇଭଳିଆ ଫିଗର ଟା ନେଲେ ଏଥିରେ ଟ୍ରାଇଙ୍ଗେଲ ଅଛି ଟ୍ରାଇଙ୍ଗେଲ ର ଇଚ୍ ସାଇଡ ହଉଛି A ବର୍ତ୍ତମାନ ଏଇ ଯୋଉ ଗୋଟେ ଡିରେକ୍ସନ A B ଡିରେକ୍ସନ ସେ ଡିଫାଇନ କରିଛି ସେଇ ଡିରେକ୍ସନ ରେ ଆମେ ଯଦି ତାକୁ A ଡିଷ୍ଟାନ୍ସ ମୁଭ କରିବା ଆମକୁ ପୂର୍ବରୁ ପିକ୍ଚର ଟା ଯୋଉ ଭଳିଆ ଦେଖା ଯାଉଥିଲା ଏବେ ବି ପିକ୍ଚର ଟା ସେଇ ଭଳିଆ ଦେଖାଯିବ it will look the very much the same thing so that's keeps the object invariant so that's why it will have a translational symmetry. The line AB is called direction of translation. The line AB is called direction of translation. Okay. And a distance defines the fundamental translation or period. The distance we shifted is A. If we distance shifted is 2A, then the fundamental translation or the period will be 2A. Okay, so the distance defines the fundamental translation or period. Strictly speaking, a body or pattern must be infinitely long in the direction of translation. जो पटे आमे ट्रांसलेट करूचे सेपटे जदि 2 मीटर 5 मीटर गला परे सरी जाउथबो ताहले आमे तो ट्रांसलेट करि परिबेनी ता माने क्रिस्टलाइन केस रे क्रिस्टल अंडरस्टैंडिंग केस रे जो पटे आमे कहूचे जो डायरेक्शन क्रिस्टल डायरेक्शन ऑफ ट्रांसलेशन जो डायरेक्शन टा को नउचे सेही डायरेक्शन रे क्रिस्टल टा इनफाइनाइट पर्यंत रहितबा दरकार हियर इनफाइनाइट मींस ए वेरी लार्ज नंबर इनफाइनाइट माने बहुत बड़ा कारण बिकॉज atomic size is in the range of angstrom huh? or unit cell dimensions will be in the range of nanometers maximum so then 10 to the power minus 9 and the crystal that we are handling is some few centimeters right few centimeters so that's why it is a very large number comparison to 10 to the power minus 9 nanometers so that's why it will almost like infinity all right. Pattern QS can be constructed by repeating the period 8 times in the direction AB. In this way, the pattern constructed by the repetition of the period is said the process translation symmetry or periodicity. Translation symmetry or periodicity. The period is repeated by integral multiple like MA, where M is a whole number the whole number 1 2 3 fraction ହେଇପାରିବନି the translational symmetry can be represented in one dimension in two dimension expanding a plane or three dimension expanding in all three directions which covers a volume so in principle every crystalline solid possesses a translational symmetry every crystalline solid possesses a translational symmetry is this clear to everybody symmetry, translational symmetry.
Yes,
Yes,
sir.
sir.
Okay, I'll take a couple of minutes, 5 minutes maybe break. Take a sip of water, and then I'll come back and we'll talk about reflection symmetry. Okay.
Okay, sir.
Okay. Okay, should we start now?
Yes, sir.
Yeah.
Yes, sir.
Okay. So next we move over to reflection symmetry. As I already have told, to understand what we mean by reflection symmetry, consider a simple triangular object. Again, it is asking us to consider a simple triangular object. Here you have a triangular object like this one, hmm, ABC, and its mirror image A1, B1, C1. Its mirror image A1, B1, C1. This one. Hmm, as shown in figure 1.3a. The line MN here, MN is the intersection of the mirror plane with the plane of drawing paper. So this is the line which is kind of cutting the plane of the paper. So that plane, so note that each point on the triangle ABC, there is a corresponding point on its mirror image A1, B1, C1. These points lie on the normal to MN drawn. What does the what is it? What does it mean? It is telling you, note that each point on the triangle ABC, each point on the triangle ABC, there is a corresponding point on the mirror image. There is a corresponding point. So if you take B, there is a corresponding point B1. If you take A, the corresponding point is A1. If you take C, the corresponding point is C1. There is corresponding point on its mirror image A1, B1, C1. Next it is telling that these points lie on the normal to Mn, lie on the normal to Mn drawn from either side and are at the same distance from it. What does it mean? If I consider A1, that will be normal to Mn. If I consider B1, that will be normal to Mn. If I consider C1, that will be normal to Mn. So whatever point I take on ABC and the corresponding point on A1, B1, C1, if I join, that, and that line will always be perpendicular to Mn. This is the first criteria. Second is the distance of A from the line Mn is equal to the distance of A1 from Mn. So, if I take a point on ABC and the corresponding point on A1, B1, and C1, those 2 points should be equidistant from the line Mn. Okay? ଯଦି ମୁଁ ଏ ବି ସି ଟ୍ରାଙ୍ଗେଲ ର ଯେକୌଣସି ଗୋଟେ ପଏଣ୍ଟ ନଉଛି ଆଉ ତାର କରେସ୍ପଣ୍ଡିଂ ପଏଣ୍ଟ ଟା A1, B1, C1 ରେ ଅଛି ତାହେଲେ ଫାର୍ଷ୍ଟ କଥା କହୁଛି କଣ ନା ଏଇ ଯୋଉ ଦିଟା ପଏଣ୍ଟ କୁ ପଏଣ୍ଟ ଟ୍ରାଙ୍ଗେଲ ର ଯୋଉ ପଏଣ୍ଟ ଅଛି ତା କରେସ୍ପଣ୍ଡିଂ ପଏଣ୍ଟ ଯୋଉଟା ତାକୁ ଯୋଉ ଲାଇନ ଟା ଜଏନ କରୁଛି ସେ ଲାଇନ MN କୁ କଣ କରିବ ପରପେଣ୍ଡିକୁଲାର ହବ ସେକେଣ୍ଡ କଥା ସେ କହୁଛି ଯେ the distance of that point from Mn should be equal to distance of the corresponding point from Mn. Okay. If you take, for example, B, 3B, 3B is like a cone. Is like a cone. So A is a 2D geometry. B is a 3D geometry. Object placed vertically, and C is again placed in a horizontal. The cones are placed in a horizontal way. From the above description of reflection symmetry, you may be tempted to conclude that if we place an object in front of a mirror and look into the mirror image is an exact replica of an object. But that is not true. The mirror usually transpose. This is important. The mirror usually transpose the front and the back with respect to the mirror plane parts of the object. It means that the mirror turns the image of an object inside out along the direction. So, what does the mirror do? It means that the mirror turns an image, the mirror turns image of an object inside out along the direction perpendicular to the plane of the mirror. Inside out along a direction perpendicular to the plane of the mirror. Okay. If one half of an object is mirror reflection of other half of a plane, the object is said to have mirror symmetrical, and the plane is said to have the plane of reflection symmetry. This is kind of very much important to understand what is reflection symmetry. If one half of an object is mirror reflection of other half about a plane, if one half of the object is mirror reflection of other half about a plane, the object is said to have a mirror symmetrical. It's said to mirror symmetrical, and the plane is said to have a plane of reflection symmetry. All right. To illustrate what I mean by reflection, by plane of reflection symmetry, let us consider few examples it is telling you. For example, if you take U, the shape U, okay, a 2D object in the shape U, then U is symmetric with respect to Mn. U is symmetric with respect to Mn, right? V is symmetric with respect to Mn. X is symmetric with respect to Mn as well as OP. Mn as well as OP. Similarly, H is also symmetric with respect to Mn as well as OP. Is this part clear?
Yes, sir.
Symmetry and plane of symmetry.
Sir, I have a question.
Yes.
What is the difference between inversion symmetry and reflection symmetry? Are they
Reflection
different?
symmetry, yeah. Let me tell you from mathematical point of view first, then I will explain pictorially. Okay. In reflection symmetry, let us say I have an object and I am taking in reflection about, let's say, x-axis or xy plane. I am taking reflection about xy plane. Okay. So then what will happen? If I'm taking reflection about xy plane, so that means my z will become minus z, but x and y will remain same. Okay, my x and y will remain same. If my plane of reflection is xy plane, let me draw and then explain. That will be more clear to you. So if I am taking x, y, z, if this is going to x, y, and minus z, can you imagine? A
Yes, sir.
point xyz is going to xy minus z. Let us try to draw it. Huh? Let us try to draw it. So let's say this is xy plane and this is my z axis where this is origin. Okay. If I have an object over here, let's say I have an object over here, and imagine this is my xy plane. This is my xy plane. If I take a mirror image, it will be somewhere here, right? Isn't it? So then what exactly is happening? The x will remain as it is, y will remain as it is, but only the z will go to minus z. Okay. But in case of inversion, what will happen? Instead of going from xyz to xy minus z, it will go x, y, z to minus x, minus y, and minus z. So it will be somewhat through the center, it will go to the opposite side. It will go to the opposite side. So somewhere here. Is it clear now?
Yes, sir.
Or in principle, if you take three mirror operations, then you will get inversion. So first mirror operation with respect to z will make it minus z. Next mirror operation with respect to y will make it minus y. And then mirror operation with respect to x will make it minus x. And the point will go from xyz to minus x, minus y, minus z. Clear?
Yes, sir.
All right. Let me come to, yeah. Let us examine here. X is symmetric about this as well as symmetric about this. But U is only symmetric about this. U is not symmetric about this line. U is not symmetric about this line. V is not symmetric about this line. You can imagine. So it has only one plane of symmetry. U has only one plane of symmetry, where X has more than one plane of symmetry. X has two planes of symmetry. H has two planes of symmetry. Okay, so that's why it is telling you that at this stage you may ask, can an object have more than one axis of symmetry? Can an object have more than one axis of symmetry? Yes, it can have. In two dimension it will be axis, in three dimension it will be a plane. It is obvious. Huh? The answer to this question is affirmative. Yes, the affirmative means the answer to this question is yes, it can have more than one plane of symmetry or more than one axis of symmetry in case of two dimension. All right. Objects can have many axes of symmetry. For example, if you take, for example, a square can have, this is one, sorry, this is one axis of symmetry, this is another axis of symmetry, this is another axis of symmetry, this is another axis, so it is four axes of symmetry.
If you take a hexagon, if you take a hexagon, hexagon will have, it has like 6 sides. So it will have three bisectors, three side bisectors that will have symmetry, and three angle bisectors. So it will have six axis of symmetry, six axis of symmetry. Hmm? If you take a three-dimensional, if you take this object, let's say three-dimensional object, three-dimensional object. Here you will see, you can see, if you take a perpendicular bisector plane to this cube, then the left half is exactly same as the right half. So it has a plane of symmetry like this one. Similarly, if you take a diagonal plane as shown here, the left half is exactly same as the right half. So it has a plane of symmetry along the diagonal. Okay, is this clear?
Yes, sir.
Reflection symmetry clear helana? Na kon doubt achi kar?
Yes, sir. Clear.
All right. Then we move over to yeah. What is next? Next is inversion symmetry, right? Yeah. Okay. So next we'll discuss inversion symmetry. Okay. As already have mentioned, in 2 dimension it will go from xy to minus xy. In 3 dimension it will go from xyz x y z to minus x minus y minus z. Okay, and you can imagine if you take this figure kind of explains because inversion is somewhat 3 dimensional, so you have to be a little bit careful while understanding it. You can see it has drawn a cube. Right? It has drawn a cube. A, B, C, D, E, F, G, H, and then after inversion, A will go to the point G. So here it was A will go to G, and G will go to A. Okay. Similarly, uh, so what will happen? Now in this case, C was here, so C will go to E and E will go to C. Hmm? So B will also, so here point of inversion point is O. About the point O, it is they are taking a, so inversion around O. That part is has to be, so inversion operation around O. Inversion operation around O. With respect to O, they are inverting. So that's why your A is going to G, G is going to A, B will go to H, H will go to B. So around the diagonal. Yeah. Similarly, E will go to C and C will go to E. So that's how exactly we are getting A, B, C, D, and E, F, G, H. So this picture kind of tells you that if I take, let's say, O to be origin, O as origin, okay, A, O as origin, and let's say the side of the cube, side of cube is equal to 2A, is equal to 2A. Okay, let me draw it and explain. Then it will be whatever I was telling. That will be much clear. Yeah? Let's say, let me draw it. Okay. So if this side is 2A, then the midpoint will be 0. So this is also 2A, and this is also 2A. So then my this point, the coordinate of this point will be A, A, because this is 0, 0, 0. This is 0, 0, 0. And this point will be minus A, minus A, minus A. All right, clear? This will be A. This will be minus A, minus A, minus A. So if inversion means if A point, this point goes here, and the object still remains same, then we call it as an inversion symmetry. Clear? All right. Rotational symmetry. Next we go over to rotational symmetry. Rotational symmetry. So what does rotational symmetry means? If we rotate by an angle, let's say theta, and the object remains same, then we call that it has a rotational symmetry by an angle this theta or 90 degree or 180 degree. Okay. So let us consider the letter N. Consider the letter N as shown in figure. Note that it does not possess any mirror symmetry. It does not have any mirror symmetry. If you take a mirror, it will not, if you take a mirror image, it will not be same, or one half is not equal to the other half by any means. Okay, but if it is rotated by 180 degree, if it is rotated by 180 degree about an axis, normal to the plane of the paper, about an axis passing through this O and perpendicular to the plane of the paper, passing through its center O, the letter would coincide with itself. That means what? Write, if I write n, if I write n, and then I will rotate it 180 degree. If I rotate 90 degree, if I rotate 90 degree, let's say I rotate 90 degree, it will be like this. If I rotate again another 90 degree, again it will be somewhat like this, right? So it will be the same n again. So 180 degree, if we rotate by 180 degree, then the object becomes the same. Okay. We can therefore say that the letter n is symmetric in rotation to a rotation 180 degree. It is symmetric with respect to rotation by an angle theta, where theta is equal to 180 degree. This is, that is, it possesses rotational symmetry. Rotational symmetry is there, but about an angle theta, which is equal to 180 degree. You can easily convince yourself that the rotational symmetry is inherent also in letter S. Yeah, if you take N, S also similar. If you rotate 180 degree, then it becomes the same again, right? When rotated in the plane of the paper. So if we consider the general, we can generalize the above observation as follows. How? If an object, if an object coincides with itself, if an object coincides with itself exactly when rotated about an axis, passing through it by an angle theta is equal to 2 pi by n, 2 pi by n, or its multiples, where n is equal to 1, 2, 3, 4, is said to have n-fold rotational symmetry. N-fold rotational symmetry. The corresponding axis of rotation is said to be an n-fold axis of symmetry. So 180 degree, theta is equal to 180 degree. That means it has 2 pi by 180. 180 is pi, right? 180 degree means it is pi. So 2 pi by pi. So it is two-fold symmetry, two-fold rotational symmetry. Let's say we take an object where theta is equal to 45 degree. Then we call 2 pi by 4. 2 pi by 4. Okay. So it will have how many? 8-fold rotational symmetry. So anything wherever we see theta, we have to, sorry, uh, we have to write down what is theta. Theta could be 180 degree. Then rotational how many fold symmetry is equal to 2 pi by theta. So theta is this is equal to pi. So this will be the two-fold symmetry. Okay. And it has been observed, this is very much important. It has been observed that we can have n is equal to 3, 4, 5, 6, 3, 4 symmetry, 4, 4 symmetry, 5, 4 symmetry, 6, 4 symmetry, like that only. Huh? এতে পর্যন্ত বুঝে না না নাই?
Yes, sir.
ଏଇଠି ଗୋଟେ ଜିନିଷ ଖାଲି ମନେ ରଖିବ ଯେ 5-4 ସିମେଟ୍ରି ହବନି ହେଲା there will not you not later in the real crystal in real crystal mathematics ଆମେ କହିପାରିବୁ mathematics there is no problem but in the real crystal case ରେ this part is very much important that this part here that uh, 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold. So rotational symmetries access are possible. 5-fold is not possible. Okay, 5-fold is not possible. 5-fold not possible. Okay. Yeah, I'll take a couple of minutes break and then I'll start with reflection rotation. Okay, let us start. Reflection rotation symmetry. Reflection rotation, this is kind of double operation. So there will be rotation and then operated with reflection again. So all these four fundamental symmetry operations that we discussed, like translation, and then we talked about mirror, reflection, rotation, inversion, all these operations can be single operated or they could be multiply operated as well. That means we first translate and then we take a mirror reflection. We first rotate and then take a mirror reflection. We first take a mirror reflection and then invert it. So all these things or all three operations consecutively that we can do. Okay, so that so basic idea is when we talk about a crystal can be looked from different angle, from different angle. So how can we say that the crystal that we are seeing and another person is seeing are same? Only if it is invariant under symmetry operations, then only we'll say it is the crystal is same crystal. Otherwise, it is a different crystal. Okay. So next we come to geometrical arrangements in crystals. Geometrical arrangements in crystals. This is what I was telling little while earlier, that lattice plus basis will make crystals. Lattice plus basis will make crystals. Lattice means it will only the points. Basis means it is the constituting atom or group of atoms or molecules like that. Here it was given NaCl. It could be just Na and Cl ions bonded together by an ionic bond. So this will be the form of crystal. This will be the form of a crystal. Okay. And this basis lattice structure are very fundamental. The basis could be different basis. I could have NaCl, it could have calcium chloride, it could have carbon, it could have silicon. So different atoms can be incorporated in lattice to a same in a basis. Sorry, uh, different atoms and molecules can be named as basis, but lattice could be the same lattice. So lattice is most like a mathematical arrangement, a geometrical figure you can say. Okay. Then there comes the concept of something called Bravais lattice. A space lattice called a Bravais lattice comprises an infinite number of points in space such that the arrangement about a given point is same as that about any other point. Okay, so let us try to understand this sentence. This is a very important sentence what it is telling you. A three-dimensional space lattice is called a Bravais lattice, comprises an infinite number of points. It consists of an infinite number of points in space such that the arrangement about a given point, is same as that about any other point. The arrangement about one point is same as any other point. This it means that a Bravais lattice, all lattice points are equivalent. All lattice points in a Bravais lattice, all lattice points are equivalent. If all lattice points are not equivalent, then it is called. If all lattice points are not equivalent, we get a non-equivalent lattice sites, non-equivalent sites in the lattice, then the lattice is called a non-Bravais lattice. Non-Bravais lattice. Okay. With the above understanding about Bravais lattice, let us now discuss its different types, the different types of Bravais lattice. Okay, in 2 dimension as well as in 3 dimension. 2 dimension as well as in 3 dimension. In 2 dimension, what are the possibilities? What are the possibilities? So you will have two directions. One is A, one is B. One is A, one is B. Okay. To specify the position of lattice point, we choose the origin of coordinates of a particular point O. And then we write the position of the lattice point P, RP. This is called lattice translation vector as well. RP is equal to MA vector plus N MA1 plus NA2, where A1 and A2 are the two vectors inclined at an angle phi, and M and N are pair of integers. What does it mean? What does it mean? Let me explain by drawing it. Okay. Let us say I have points like this. I have points like this. All right. I have points like this. Hmm. So this is, let's say, A1, and this is, say, A2. Okay. I want to go from this point. This was my point of interest, and then I want to go from here to here. Let's say here. So how much translation I have to do? I have to go A1, twice A1, thrice A1. So this will, if this point was 0, 0, see, this point will be thrice A1, and this will be A2. Now it is telling that this 0, 0 and 3A1 and A2, this point should be equivalent. These 2 points should be equivalent. Then only we will call it Bravais lattice. And possibility, what are the possibilities? A1, normal possibility. So translation would be, translation in this will B or R, whatever. In Charles Kittle it is P, and in this, in the material that has been given to is B, I think that. Okay, it doesn't matter. Translation vector. This will be equal to m times a1 plus n times a2, where m and n are just numbers, just numbers. Okay, and the possibility that a1 and a2 are perpendicular to each other, or they are making an angle theta between them. A1 and a2 could be perpendicular to each other, or a1 and a2 might be having an angle theta between them. A1 and A2 might be having an angle theta between them. All right. So based on that, we kind of categorize or classify these lattice structures, Bravais lattice structures. So we take first example of this one. Okay. Depending on the magnitude of basis vectors and the angle phi between them, we obtain special cases of 2D Bravais lattices. For example, A1 is equal to A2 and phi is equal to 90. We have a square lattice. If A1 is equal to A2 and phi is equal to 90, then we call it a square lattice. A1 not equal to A2, but phi is equal to 90. A1 is not equal to A2, but phi is equal to 90, then we call it a rectangular lattice. If A1 is equal to A2 and phi is equal to 120 degree, like in this case, it will be called an hexagonal lattice. It will be called an hexagonal lattice. Okay. And in general, it will be called an oblique lattice. In general, it will be called an oblique lattice. All right. Now, the vectors A1 and A2 encompassing the primitive cell are called primitive lattice vectors. What is a primitive cell? Primitive cell, what do you mean by primitive cell? That is very much important. Now, we try to understand from here. Note that all the cases shown in figure, a square or a rectangle or a parallelogram represents the smallest unit, the smallest unit. The important factor is the smallest unit, smallest unit. Huh? The smallest unit that may be represented that may be represented to construct a complete lattice. Here each unit cell has one lattice point at each of the four corners, but each point is shared by four adjoining cells. So there is only one lattice point per cell. One lattice point per cell that I have drawn earlier also. One lattice point per cell. And that kind of cell is called primitive cell. That kind of cell is called primitive unit cell. These kind of vectors A1 and A2 are called primitive lattice vectors. Primitive lattice vectors. Is this clear to all of you?
Yes, sir.
Okay. So this is one way of constructing the primitive cell. Another way of constructing the primitive cell is Wigner's construction of primitive cell. What does the Wigner's method of constructing primitive cell is very interesting. Let me draw on my notes. Then it will be quite clear to what is the difference you can see. Uh, suppose I have points like this. Okay, what is it? I have points like this, like this, like this, like this. Okay, so what I told that I can take this to be my unit cell or primitive cell, this to be my primitive cell, or what I will do, I'll take a cell like this. So where I have only one point in one cell. Okay. Another way, another way is that we have these points. We have these points. Okay. We have these points. And then what I will do, let us say I have this point, the nearest neighbors. I will take this is one of the nearest neighbor. This is another nearest neighbor. Next nearest neighbor is this one, this one, this one, and this one. I will take the perpendicular bisectors of these lines. So one will be this one, another will be this one, another will be this one, another will be this one, this will be this one, this will be this one, this one, this one. So you can imagine somewhat like the space is somewhat like you know like this. Okay. So that will be deductions from here. My drawing is not that clear here also. So that is what it is. It is drawn here. I can show you. Mm, If you come to this figure, huh? If you come to this figure over here, so it has taken the perpendicular bisectors. You can see this is the center point. This is another point. This is the bisecting line. This is one point. This is another point. This is the bisecting line. Huh? This is one point. This is one point. This is the bisecting line. This is one point. This is one point. This is the bisecting. You can tell what happened to this bisecting. This point and this point and this bisect. This bisecting line is outside, so it does not contribute. So similarly, this point and this point, the bisecting line is this one, and this point and this point, the bisecting line is outside maybe. This point and this point, bisecting line is this one. So this region over here, this is the this is also a primitive cell, and this primitive cell is called Wigner's primitive cell. It also has one lattice point per primitive cell. It also has one lattice point per primitive cell. Okay. All right. Up to this point, any question, anything? I think it's possibly time now. To discuss about three-dimensional Dravius, that is possibly in the next class because we cannot leave it halfway through. If you have any question, you can ask me now. Any doubt, any question, you can ask me now. Any question? So all of you have this study material with you, right? In the PDF form or in the book form?
Yes,
Sir,
sir.
PDF is available with us.
Yeah. So I suggest, for tomorrow's class, at least whatever we discussed today, that you go through it little mindfully, yeah? Because based on that, we will discuss tomorrow. Three-dimensional lattice and other things. Because it's very much important to understand what is base lattice, what is basis, and what are the symmetry operations and all. Because later on, we'll just be telling what kind of symmetry we have. That time you might be wondering what is rotational symmetry, what is inversion symmetry, and all. So it's a very basic thing and not so difficult to understand actually. Only thing is you just have to read little. Okay. Any question? Any suggestion from your side? If we if you think anything can be done extra, anything any, that I can do more.
Sir, your teaching is really nice, but the problem is that we are getting very less classes. You have just taught as we wanted you to teach. Means we were just waiting for this kind of teaching, but the problem is that we're getting very less time. Means will you take more than 4 classes or 4 classes
Yeah,
only?
well, this is not controlled by me. This is kind of assigned by the IGNOU Study Center at Bhubaneswar. So you can possibly talk to them. Okay, you can possibly talk to them if they want. I can take. It is up to them. It's not in my hand because they are kind of moderating it.
But
Okay.
in 4 classes, we cannot cover this whole thing.
Yeah, I understand. See, this is not actually regular class. This is kind of counseling class. But I think, I mean, from my side, from teacher's perspective, if I do not tell the basic things, there is no point in superficially telling all the things, right? So that's why I thought maybe I will start explaining everything from the beginning so that it is kind of the building block or the foundation so that later on when you read the material, you will be able to understand. Because if I directly go to lattice vibration or different types of lattice and all without explaining these things, then there will be a lot of questions in your mind what exactly is talking about, right? So I understand this is like one semester course and it cannot be done in 8 classes or 8 hours actually. So 4 classes. So but this sessions will definitely help you for your further reading. Once you start reading on your own, that will be you will be able to understand. I believe. And rest you can talk to the study center, whatever they decide to, because I have no control over that. Sorry for that.
So just you can means just make the things like which you think that we should know from you. We need your guidance. Like you have selected this and explained it nicely.
Yeah, yeah, I understand. So I
Thank
will the things that I will be discussing in detail that will
you.
be very much required to understand other parts. Okay.
Yes.
Let it put it this way. So whatever I am discussing, that will be very much essential uh, for you to understand. Later on, the parts which I might be skipping or I might be telling that you can read, that parts you can read and from my teaching you can understand.
Okay. So
Sir, one request.
Yes.
Sir, the lessons you are teaching or about to teach, please sir, make some notes and provide us. That will be really very much helpful during our exam time.
Yeah, see,
Sir,
actually, see, your study material itself is a note, actually. Your study material, because if you look at the books, those are huge. Your study material, whatever they have made, is actually like notes only. And those who are thinking about notes, I would suggest, and personally, I suggest that you just read the study material. That is very well written, in very simple language. It is not any difficult English also there. So you will be able to understand. And whatever doubt you can ask, you can discuss. That is fine. You're getting my point. Because notes means, I mean, this is not only the study material is notes only. If you, I can maybe tomorrow I will show you the book. In the book, they have not explained in detail these things. Here they have nicely explained in detail. Okay, so that will not be an issue. So, my personally my suggestion is don't look for other notes. Rather, just concentrate. I mean, if you cannot read other books, that's fine. But concentrate only on the study material. That's well written, and if you can understand everything from the study material, that is enough actually. That is enough. It's a nicely written study material.
okay, sir. Thank you, sir, for your suggestion.
Okay. Okay. So we'll possibly stop it here now, and we'll meet tomorrow at 6 a.m. 6 p.m.
yes, yes, sir. Thank you, sir.
Yes, sir.
Okay.
Yes, sir. Thank you.
Have a nice time.
Good night, sir.
Good night.